I hope I am live. Let's check. All right, it says live. 07. Yep, I'm live. Hey everyone, I am Ashish. Welcome to the AI Bootcamp. So, right now we will be talking about classification. And as usual, we're going to go to cookiesensor.com and launch labs. Magical labs, Harry Potter labs. We're going to open the labs. Okay, code server. Classification we are supposed to do. No, we are supposed to do clustering today. Yep, clustering we are gonna do. So first of all, okay, what's clustering? So far, we have been talking about regression. We have been talking about classification. So the data sets that we had, they had features and something to predict. That was target. So we had question in form of features, we had answers in form of target, and we said, okay, I'm throwing you some questions and relevant answers. So next time when someone asks you a question, learn the behavior of the pattern and answer the question accordingly. But in clustering, what happens is there will be data of anything really. And what you would be doing with that kind of data is sort of grouping that data into some clusters. So, like, let's say if you have a lot of data of, let's say if you're talking about the churn data, the telecom data set. So, over there, clustering would make sense if we are to group the entire data into two groups of people who would default or people who would not default. I mean, churn or not churn. But like, let's say over here, we will be taking this cars data set. And this is how the cars data set looks like. Miles per gallon, number of cylinders in a car, replacement horsepower. What's this? Right. If you are from automotive, you would understand what this is. I am from automotive, but I don't understand what this D rat is. DRAT. Okay. I think this should be the weight. You said quarter second VS, whatever. The point is we have a data set over here and we want to take a look at behavior of the data in a way that, okay, how many data points are similar and how many data points are like not so similar. So in this respect, what we do is first of all, imagine a plot, we draw a plot and take a look like this. Okay, this is how the entire data set looks like, and sort of we can see that there is one sort of cars which are over here in the purple shade, and another sort of cars or another sort of groups which are in the shade of yellow. And then there is this another shade which is in this kind of diagonal. So you can see there are some three or four groups here. And I can imagine that there are three or four groups because one category of car could be the normal production category that normal people use. One could be sports car, one could be SUVs, and so on. So those could be the clusters. So we will take this data. We will understand this data in a form that, okay, Mazda, as I remember, Mazda six cylinder must be a sports car. Okay. Mazda RX-4 six cylinder must be a sports car again. Datsun 7110 four cylinder, but I don't think it's a sports car. But take a look. Hornet Sports Bout. It says sports in here, so it's eight cylinder. So in a nutshell, what we do with clustering is we group similar looking data points and we analyze its outcome or its aggregate, sum, median, count, and so on. Like let's say cluster 0 has a mean of 15 miles per gallon. Cluster 1 has a mean of 20 miles per gallon. Cluster 2 has a mean of 18 and cluster 3 has a mean of 28. And right about as I can see over here, cluster 2 and cluster 1 are very much similar. 18, 20. So maybe we could have kept only three clusters and would have been fine with it. Let's take a look at another differentiator, which could be the median. So median of 15 And this is the miles per gallon we are talking. Median 15, median 19, not so much of a difference. Let's take a look at the cylinder capacity. So number of cylinders, we have 8, 5, 6, 4. 5.14 doesn't really make any sense. So it could be either 5, it could be either 4. So I should have maybe kept the number of clusters to 3 only, because I can see that cluster 0 is on its own very much differentiable from cluster 1 and cluster 2. And cluster 3 is very much differentiable from the other clusters. Just like we had visualized now over here. Like there is a cluster on the right, there is a cluster on the left, and there is a cluster on the middle. So maybe we can keep only 3 clusters, and let's do it. Yeah. Let's say if I were to keep only 3 clusters, okay, then what would be the outcome? I'm gonna do a run all. It's taking some time to run all. Oh yeah, done. So take a look. The moment I select 3 clusters, now it's saying that first cluster has a mean of 25, second has a mean of 15, and third cluster has a mean of 18 miles per gallon. Okay, so that tells me this highest miles per gallon could be the your city car, your city car. I mean, your regular car that regular folks drive. This cluster one may be those cars which are expensive, which are like sports car with the least miles per gallon. And its cylindrical data also suggests we are saying is right. So 4.3 is your average middle class car, 7.7 on the cylinders, meaning it would be 7 or 8 cylinders. So that's a sports car category. Yep. And what else? Displacement, 341 cc, I believe it would be, but sports car are way more than 341 cc's. But okay, in general, it's saying I should have also kept highest and lowest. So let's also add a highest, maximum. I hope it is right. Minimum. I hope it is right again. Just attribute error series dot group by has no maximum. And it should be max. And if we are wrong, then we will just check out the pandas documentation because, ah, yep, it worked. So in the displacement category of the cluster 1, we have mean displacement of 341, maximum displacement of 472, and minimum of 225. Meanwhile, take a look. The minimum horse, this is the displacement. Minimum displacement of the cluster 0 is 71 only, which suggests it is a commercial car for regular use cases. Or I can say, if not a sports car, I mean, 4774 on the displacement side, it's not really a sports car category, but it could be a SUV category. It could be a BMW kind of category, right? Even if they are not sports car, there are BMWs of 8 cylinders and 6 cylinders, but there are not BMWs of 4 cylinders. Definitely not. So, clustering in a nutshell gives you a mean to basically visualize similar looking instances and then analyze. Okay, one cluster is having some properties, cluster number 2 is having some properties, and cluster number 3 is having some properties. It could very well be that there are no clusters at all. Like, let's say if you have clothes and you are grouping the clothes into 3 clusters, one cluster could be the small size clothes, one cluster could be the medium size clothes, one cluster could be the large size clothes. So I'm selecting 3 clusters, and I'm grouping the entire instances of data into 3 records. First being small size, second being medium size, third being the large size. And there you go, clustering. So the point is we don't have the target variable in here. And when you will do this kind of analysis, now you would get more understanding of okay what this clustering is. So first of all, let's generate some synthetic data set. So in sklearn only there was this make blob functions, make blob in sklearn, which is used to generate synthetic samples. Make blob sklearn, and I'll take you to the code. Yep. So make blobs and number of records to keep 400, number of centers to keep 4, standard deviation 1.2. I'm just choosing that to be. It could very well be any other standard deviation as well. Random state 42, so that your synthetic data is same as my synthetic data. That's why the random state argument is important. So it gives you two things really. A tuple of x and y. We won't be taking y in consideration over here because we are trying to do clustering on the x component, not the y. We are not trying to predict anything right now. So if you visualize the data set, I can visually tell that there are three definite groups, four rather really, but three are very definite. Like first group is over at the top left side. This is the second group. This is the third group at the rightmost side. So there are multiple techniques of clustering. And how do I know it? It's because I read the documentation, and so should you. sklearn documentation is not something you would read like a novel or something, but it's more like a dictionary that, okay, I've forgotten this word, so let's go back to the dictionary and take reference. So usually with time you get to learn, okay, you get to understand what this documentation is about. So I'm going to the sklearn documentation homepage, then selecting the clustering part, and there you'll go. You will see a lot of clustering types, basically. So there, let's take a look at this. I hope it is visible at your end. Ah, I believe it is visible now. Okay, so see, take a look. Let's say I have two data points, two groups of data points like this. Over there, k-means, some algorithm called k-means is not able to perform good because it's saying one group is of blue color, one group is of red color, but I can clearly see that one group should be this inner circle, one group should be this outer circle. So over there you can see like which kind of data or which kind of data really would support which kind of algorithm. So let's say in this case, this DBS scanning, density based scanning, is working out fine. HDBS scan optics is working, Bursch is not working, Gaussian mixer is not working. So what else? Spectral clustering is working. My point being, you don't have to get into the nitty gritty of each and every algorithm. You just have to look at the diagram and understand, okay, if I visualize my data like this, or if I visualize my data, which I have done, really, my data is visualized like this. So in a pattern like this, which sort of algorithm would work the most correctly? So my data pattern is something like this over here. And over here, I can see there are three clusters forming, and this algorithm is k-means. So k-means works well when the data is separated like this. When our data is separated like this, so I would apply k-means. My point being again, you at least in the initial stages, you don't have to understand each and every working of all these algorithms. Just understand basics or intuition of one, and we will be understanding intuition of k-means only. And then just take a look at the graph and then just decide, okay, which according to the data, which algorithm you should follow. Let's take a look. The kind of data that we have, our data has numbers like this much, na? So k-means work, the second one work, third one works, and these sort of algorithms are not at all working. Not at all working. Which are these two? Agglomerative clustering and DBS scanning. Not at all working, right? So yep, there you go. The simplest. This is the like simplest cheat sheet, and let's go back to our own data. So I have over here about three or four clusters really. Like saying we have three clusters wouldn't be wrong. Saying that we have four clusters wouldn't be wrong. It's really our objective how many groups we want in here. So just like in the scikit-learn API, we have, like, let's say if I choose k-means, so the k-means algorithm, some mathematics really, I don't. care about this kind of mathematics, nor should you in the start or in the beginning. You shouldn't care about all these mathematics as well. So I am at the k-means. Where is the API of how to use it? How to use it? Method name k-means. Okay. Oh yeah, there's also silhouette analysis, kind of this thing which tells you how the optimum grouping should take place. Like if you're selecting two groups, these two groups shouldn't be like this way. Like one group is very short and another group is very big. Anyway, I was at k-means clustering. Array, where is the code? I think I'm at the user guide, not at the API. So I will write k-means sklearn, and the class that I would search for is k-means sklearn documentation. Yeah, right here. So k-means, so the import statement we have seen above, and let's see the usage. So from sklearn.cluster import k-means, then numpy import as well to just create a synthetic data. How do we call the k-means? Call the k-means class, assign the number of clusters. Like we have to assign the number of clusters we want to group into, at least in the k-means algorithm. In other algorithms, like DBS scanning, you don't select how many clusters to make. Algorithm will decide how many clusters you would be making. So right now we will be studying only k-means, and the point is k-means choose number of clusters as 2. I hope it is visible, or otherwise let me make it a little big. Perfect. So k means number of cluster is 2, random state is 0, and init auto, and init, what was that? Auto initialization. No, auto no. I don't use auto. I use some other initialization method. Hmm. Basically, the initialization method is how you would start. Yeah, the best initialization method that I have seen as this k means plus plus. It's an algorithm to decide where to start the initial, you could say, parameters from. I know it's not right to call it parameters, but it's okay. At the beginning, you can just say, first of all, initialized random parameters, then use some methods to reach or minimize the errors and find the right set of optimal clusters. Like let's say if I'm over here, if I'm over here using the k-means algorithm and have selected, let's say, 3 clusters. So my 3 clusters would be initialized in such a way that very much randomly, like one cluster could be over here, right, right here where my cursor is. Second cluster could be here. Third cluster could be over here. Three random points. But all these 3 random points could have been overlapped as well. So random initialization could very well act good in certain cases, but could very well hurt our program in other cases. That's why we usually choose k means plus plus as the initialization, because k means plus plus, what it does basically is that it tries to ensure that all the clusters that you assign randomly are kind of far away as possible. And then let's say you have chosen one over here, and one over here. Then this particular cluster will see, okay, which kind of cluster is very much closer. So it might be getting assigned to this. This cluster over here that we selected, it might get selected to this. This particular cluster that we had selected, it might get selected to this. And maybe it would all come something like this. Had we chosen 4 clusters, this would be the grouping outcome. Number 1, 2, 3, 4. And there is an album method, and you can get the API of the album method on the documentation. But what really happens is we calculate the distances of cluster. Like let's say one cluster is formed over here. Then I want to calculate the distance of this particular centroid with all the data points, and so on for all the 4 clusters that we have. So inertia really means sum of all the errors that we have. So my task is to minimize the inertia, minimize the errors, but in such a way that I don't really create a lot of clusters. So there is a elbow method, and wherever you find the elbow kind of following the same pattern. There you would see like, okay, like at the most four clusters should be there, at the least three clusters should be there. That's what I can figure it out, because error is dropping very fast till three. But after three onwards, the error is not dropping very fast. Error is more or less the same. So you could have very well said, let's keep three clusters, let's keep four clusters. The point would be, analyze what you are doing with clustering. It doesn't matter really like how many clusters you are assigning. What matters is what analysis you are doing with that kind of clustering. So this is the DBS scanning. In DBS scanning, you don't really start with, okay, like how many clusters to create. You start with something called epsilon. You start with something called minimum samples, like how much samples should be there for a cluster to be called a cluster. I want it to be a cluster only if there are five or more examples. That's what this means. This epsilon value I don't really know or care about. I usually go and hit and trial something like this. I would hit and trial with something like this. I mean, I do know epsilon, what's epsilon, but I don't really care for it. For I in range of, let's say 10, not 10, rather it's a decimal value, right? So I would say something like 0.1 and 0.5. Let's follow the documentation to see the optimal value of this epsilon, because I'm forgetting what this epsilon really is. VBS scanning, Sklearn, and you will also be forgetting. Don't judge me if you're thinking like I'm forgetting all these algorithms. You would be forgetting all this time. So default value of epsilon is 0.5, and let's see what the epsilon is. The maximum distance between two samples for one to be considered as in the neighborhood of the other. This is not a maximum bound, blah blah blah. This is the most important BBS parameter to choose appropriately for your data. But then again, it's saying that it's the most important parameter. Yes, I know it's the most important parameter, but you don't initially know the best value of it, because you have to decide it where, yeah, you have to decide it. Like first you would try with, let's say 0.1, then you would try with something like 0.5, then you would try with something like 0.7, then 0.9, then maybe 0.3. And then you would see, okay, what's the ideal pattern? So over here, what I'm doing is I'm creating a for loop, and I'm putting inside the for loop all of these things. And let's say I'm adding 0.3, 0.5, and for a very well fact, I know that 0.7 was a good case study for it. So, and let's also print somewhere along the line, like what's the, like right now the syntax goes for I in range of 0.1, 0.3, 0.5, 0.7. DBS scanning for me, epsilon the value of I, and minimum sample split is 5. You could also say something like this. Another for loop for uh, j in range of 4 to, let's say, let's keep it 6 only, because otherwise it would be very big. So two for loops. And yeah, basically you don't really know what parameters to select. Either you could hyperparameter tune it, or you just take two for loops inside and go with something like this. So BBS scanning result. I'm gonna choose F string over here, and then I will say something like this, like epsilon value is this I, and minimum samples value is j. Let's try it out. Okay, so a lot of plots have been made for me. So we gotta analyze them one by one. See, first of all, I tried epsilon value of 0.1 and then minimum sample split of 4. Entire data is grouped as just one cluster, not accurate, which is not at all accurate. Just like I told you in DBS scanning, now you don't really know like you wouldn't know what's the best parameter to start with. So you take a blind guess, then you iterate over it. Okay, I know for a fact right now that epsilon of 0.1 is not giving me anything at all. So I'll try with something else. I'm trying with epsilon of 0.1, then minimum sample of 5. No change. Then I'm saying epsilon of zero point 0.3, minimum samples 4. Some changes are there, but not good. Not good. Right? So let's take a look at what's the ideal situation. Let's try to find it. One by one by one by one. Okay, this kind of group looks kind of better than the others, right? So it just happened to have the epsilon value of zero point 0.7 with a minimum sample of 4. So I didn't know, okay, I needed to start with this kind of parameters. I just tried out bunch of parameters and then I figured out, okay, maybe this is the right set of parameters for zero point 0.7 and 4. Let's see what happens on zero point 0.7 minimum sample 5. So I think it's improved. Is it? No, not really improved, but more or less the same. So that's how I figured out, okay, the epsilon value of zero point 0.7 and 5 is the best case over here for the clustering that we are trying to do. All right. So the real world case is take any kind of data set and just try to perform clustering over it. And remember that depending on the clustering algorithm you're choosing, right? So you would need to scale the data. We haven't not really discussed scaling. So let's discuss scaling at the moment. Let's say I have a range of 10 and I'm creating a list out of it. So my range is going from 0 to 9. And let's say I have another range which is going from let's say 1000 to 5000. And how many numbers do I want? I want in a step of 500. So 1, 2, 3, 4, 5, 6, 7, 8. So 1. I need 10 numbers. I have 1, 2, 3, or let me just call it 0. All right, I believe these are 10 numbers now. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 10 numbers. Great. Let's say that one column we are having 0 to 9, another column we are having 0 to 4500, and it could be very well mm, just because, oh no, we will discuss it more when we have a project at hand. Then it would make more sense. But really, what I'm trying to say over here is, let's say this is the feature 1, and let's say this is the feature 2. Just because the value of feature 2 is in greater numerics doesn't mean feature 2 is more important. That's what I'm trying to say. Let's, what do I mean? So take a look. Slender column is having 6, 4. Let's print out the empty cars data set. Empty cars df dot head or dot sample. Give me a random sample of 10 values. So let's take a look. This VS, this AM gear, number of gears, 3, 4, and then displacement is in the range of hundreds, 400s. Then miles per gallon is in range of 10 to 20s. My point being, each of these features are equally important. But if you were to give all these features inside an equation like this, which would be something like y equals uh, a, let me just pronounce it. The equation would be something like y equals a0 x0 plus y plus a1 x1 plus a2 x2 plus a3 x3, where a are the parameters and x1 x2 x3 x4 are the feature names. So my point would be algorithm would somehow learn that displacement and horsepower are more important than say this drag column or q second column. Why? Because displacement is having higher number, horsepower is having a higher number. Just because horsepower is higher than this WT weight doesn't mean it's more important, right? So my point is sometimes we need to scale the data into a version that would say to the model, okay, all of these features are equally important. And how would we scale the data? I don't remember the API, so I will just Google for you. Scale sklearn. Standard scaler is there, normalize is there. So standard scaler, I'm not gonna go to the theory of it, at least not at the moment. Let's just take the value, take the import statement, as it is. Okay. Yeah. So I have the import statement right here. I'm saying scalar equals standard scalar, and then I'm saying scalar. Hey scalar, take a look at my data, and my data is empty cars df. Take a look at the data frame. All right, now it has taken a look at the data frame. Now I would say transform the data. Now you would see that something is returned, but I need to create a df out of it for it to be more uh, appealing, or it doesn't make sense right now. Like what is this output? E to the minus 1, e to the plus 1 somewhere is written, e to the minus 1. What is this scientific notation? It means that 10 to the power minus 1. What exactly it is? Let's take a look at that. So I'm going to create a data frame out of it. pd dot data frame, and then I would say that this is nothing but columns of my empty cars data set. Dot columns would just give me the names of columns. Dataset object has no columns. Okay, so take a look. What initially looked like this, where miles per gallon was in range of, I can see 10 to 30s, cylinders was in range of 4, 5, 6, and displacement was in range of 70 to 500 maybe. Horsepower was in range of 65, 62 to, I believe, 205 to 30. And then all of these other numerics were in range of 0, 1, and so on. My point is, now the same data is in the range of -3 to +3 sigma. Sigma means standard deviation. 0 means that I have 0 centered the entire data. So 0 centered, what does 0 center means? So first of all, let's take a look at what this data is about. This data is going from -3 to +3. The mean of the data has become 0 now. The standard deviation has become 1 now. And if you don't understand what standard deviation and mean means at this stage, it's totally fine. I'm going to tell you right now. So let's take a look at this thing. I will say that one feature is going from 0 to 9. Second feature is going from 0 to 4500. Let's create a data frame out of it, because why not? So I will say pd dot data frame, and let's give it the first column of A, and the first column is this thing, and the second column of B, I by mistake pressed enter, is this thing. So I have this data frame where feature A is ranging from 0 to 9 and feature B is ranging from 0 to 4500. At the moment, if you put the data set as it is inside the algorithm, then my algorithm would be like something like this. It would show or output. If it's regression, if it's classification, doesn't really matter. I'm just drawing a standard equation of, let's say, A, or let's say A1 times the column A plus A2 times the column B. And now take a look. B is in the range of thousands. So my point is, my A, the value of A is in the range of 0 to 9. So very well I could write it something like, let's for example say 5A1. And meanwhile, my middle value of, like let's say I'm taking this fifth row. So fifth row is 5 times A column, not even, but 5 times A column. 5 times A column, 2500 times the column B. So my point is the algorithm is stressing a lot of weight onto the column B just because its numerical value is high. That's why we need to make sure that both of the columns are treated in the same way, in the same important way. Like let's say both are important, but equally important. So I would say scale the data. I would say scalar 2, and then I will call standard scalar, and then I would say scalar 2 dot fit. Take a look at my data frame. Let's create a data frame out of it. df1 I would call it df1. All right. Take a look at df1 and then transform scalar 2 dot transform df1. And I know this output doesn't really make much sense right now, so let's convert it into a data frame. So again, I would say pd dot data frame. This is the output, and the column names are columns equals df1 dot columns. So take a look. Our mean would be 0. So the mean of the range from 0 to 9 should be 4.5, right? So around 4.5, we have the value closest to 0. And over here, around 4, this around this 2000 or 2500, we would have the value closer to 0, right? So my point being, the mean has become 0, and accordingly plus minus standard deviation is going on, and the entire range is going from -3 to +3. But the point is, the entire range for the column A and B are now same. So my model would be treating both of these columns in the equally important way. So that's why we sometimes scale. But just because I'm scaling it right now doesn't mean that every algorithm needs scaling. So how would you know that some algorithms need scaling and some algorithms do not need scaling? That is something you would need to read the documentation for. Okay. Or I would say something like this. Does DBS scan need scaling? DBS scan does not require specific number of clusters in advance. No, that's not what I asked. Yes, DBS scan generally needs feature scaling. There you go. Even if you do not understand the mathematics behind it, you can fully totally work with the machine learning models. That's what I want to tell you right now. And I believe let's close the session now. We have discussed, I believe, all the important points. And the GitHub repo is right over here. If you have forgotten, go to Cookie Sensei overview or the repos. I have pinned this repo 14-day bootcamp over here. And we are working with this file right now, which is in the machine learning section of clustering, the final module of the machine learning section. After this, we will be starting the deep learning section, and we will be discussing the one of the most important and I would say talked about data set, which is the MNIST handwritten data set, which is like a toy data set that everybody has worked on. So if you're in machine learning and you haven't really heard of MNIST, then I have no idea how to help you. I'm helping you. Okay, okay, okay. So all right, I'll see you in the next session.